So today I'm going to talk about formal verification and Linux kernel code. So last year, this talk was sort of motivated by a talk that I saw last year from Chris, we all saw, or some of us saw at least last year, from Christopher Waldrefson. He told us about verifying the absence of buffer overflows and other undefined behavior in C. So at the time I was thinking about what could I do somehow to actually apply formal verification to actual Linux code? Should it be, I mean, in general, the C language is considered to be very problematic. It has, you can have pointers that point to everything. There's problems of concurrency and so on. So I thought maybe we should translate the code to some other more easy language to verify, something like that. But based on this talk, I decided to just plunge in and follow up on the approach that he proposed. So this is kind of a report on what happened when we tried to do that. So basically the idea of verification is that you write a specification of what the code is supposed to do, and then you give the specification and the code to some tool, and the tool is going to figure out if the code actually matches the specification. Okay, so it's not like a magic bullet. It's not going to solve all problems. It's not going to ensure that all code is correct, because of course you can just write the specification wrong and then it will happily prove that your buggy code is doing the wrong thing. But the idea is maybe you can raise the level of abstraction of your code a bit, and maybe you can think about your specifications, and at least you'll be thinking about your code in a different way, and maybe that will provide some value. Yeah, so this is what I was saying. Can we do this kind of verification for the Linux kernel? The positive aspects is when we start thinking about our code in a different way, we might have some insights about what it's doing. And then after that, when we have succeeded in our verification process, we still have these artifacts left over, which are the specifications, and we can use those to provide some kind of formal, unambiguous description of what the code is actually supposed to be doing. So you can contrast that with comments, where sometimes there's no comments, but sometimes there are comments, but you somehow don't understand the world view of the person who wrote the comments, and so you can't figure out what they actually mean. On the negative side, of course, creating specifications is hard. And then in the context of the Linux kernel, there's also the problem of maintenance. The code is going to be changing all the time. Are we going to have a new tool and new things to think about and new burdens on the maintainer who's updating the code and so on? As I mentioned, there's no magic bullet. The specifications could even be wrong. So the idea of this talk is not to say, I think, or you should go home today and start writing specifications for the code that you're working on. The point of this talk is just kind of a thought experiment. So you shouldn't be thinking, yeah, I don't want to write a bunch of formulas. This is going to be a real nuisance. This is not going to give any benefit, and so on. The point of this talk is just to spend the next 40 minutes or so thinking about what would happen if we did this. Is this a direction that would provide some value? And can we somehow in the future find a way, if it provides some value in some way in the future, could we try to be going in that direction? Okay, so this is one of the examples that those of you who were here last year have seen already. So we have the swap function, takes 2 arguments, and the goal is to swap the values in those 2 arguments. And so we can think about what are the things that we would like to ensure about this function. And so one thing is that these arguments are pointers. We know that pointers can be null. So that would be bad for this function because it doesn't actually check for that. There's also some pointers. Pointers could point to some extremely strange address where we're not allowed to write to. And this function is also not checking for that. So there's some assumptions that we have on the way into this function about what are the meaningful inputs that we should have. And then there's also some assumptions that we have about this function about what effect it should produce. So we have some meaningful inputs, in particular that our arguments P and Q are pointers to readable locations, readable and writable locations in memory. And then the effect that we want to produce is that the value stored at the P location should be the old value at the Q location, and the value stored at the Q location should be the old value at the P location. So it's pretty straightforward. Okay, so then we have our verification tool, which is pharmacy. And what we need to do with pharmacy is we need to annotate our source code with what are called preconditions and postconditions. So preconditions describe the state on the way in, and postconditions describe what the function is supposed to do. And then when we get that information, then pharmacy will go look at all the different lines of code, and it will somehow compare those to the pre and post conditions and figure out what formulas need to be proved to ensure that the post conditions will hold based on the preconditions. And then you don't even have to do these proofs by yourself. The pharmacy connects to a bunch of existing tools which are called SMT solvers, and they take formulas and figure out whether they take basically a bunch of information. They do some kind of search around in that information and figure out whether the thing that you're trying to prove is among the set of known things. And then if everything is okay, it will say, yes, your code is good. So here now we need to write our preconditions and postconditions. We already thought about the things that we want to do. Now we put them in the proper notation for pharmacy. So our preconditions are that the addresses referenced by P and Q are writable. So these are called requires. These are things that we require about the input on the way in. So we have requires, and then we say valid P. So valid P means that the address P is an address, and that when you dereference that address, we are able to both read and write it. So that's the thing that we want. There's also valid read if you only want to be able to read it. So we need that for P, and of course we need that for Q as well. So that's for our preconditions, and we have postconditions. Our postconditions are supposed to be that we're swapping the two values. So we have ensures. Ensures describes what we want the function's activity to ensure, so on the way out. And we have what we want to ensure is that the value referenced by P is the original value, so it's called the old value of the value referenced by Q. So actually pharmacy can refer to any of the values that exist at any point in time using different labels and so on. And so then we get the same thing, of course, for Q. Q would end up being the old value of P. So these are the different conditions we want to satisfy, kind of written out individually. This is what it looks like in reality. So you have your function, and then you put a comment in front of your function, and the comment expresses the different properties that you want to ensure. So there's one I didn't talk about, which is assigns. You also have to describe the external locations that might get modified by the function, in case you're using the function in some other context. And so we write this, and then we push the button with pharmacy, and it prints out this. And so it's actually quite verbose, and most of the information is not super useful. But the important part we see here, it says prove goals 10 out of 10. So then we feel happy. We have succeeded in proving that our swap function does what we expected it to do. Okay. Are there any questions at this point? Okay. So now we'll turn to the Linux kernel. So the Linux kernel, I'm sure you're all familiar with. It seems like it's quite reliable. For example, at home I have a server. It's been running for 265 days, and I think it's only 265 days because they were shutting off the electricity 265 days ago. No problems at all. But actually, as you'll especially see in the next talk, the Linux kernel is actually full of bugs. It's kind of amazing how something so Swiss cheese-like can actually function. So many of these bugs are concerned with kind of well-known patterns, like issues in C. We have null pointers. We might accidentally dereference them. We have to manage all the memory ourselves. We might forget to do that, and so on. So there's a bunch of tools that also are used quite actively in Linux kernel to help us with that. Smatch, coccinelle, coverity, all the other things as well. So that's fine, but some other tools are some other bugs are very specific to a particular algorithm. So the person who wrote the code had a particular intention, and the code that they wrote doesn't actually match that intention. And so tools like Smatch and Coccinelle and Coverity are never going to be able to find these kinds of bugs because they have no idea what the intention is. So that's where these specifications come in. This is your opportunity to express what your intention is, and then some tool will figure out for you whether your code actually matches your intention. So maybe we can use verification to find these bugs. And I would kind of emphasize this, like, I mean, some of these bugs, at least that we look at in the scheduler, they're not causing the code to crash. They're not causing like really obvious problems that are really easy to find. It's like the little subtle things that kind of degrade your performance over time. Like bad decisions, you implement some algorithms not really doing exactly what you thought. So this is an attempt to help with these kinds of issues. So the obvious challenge is that verification is very hard. There's some hope because people have recently done some experiments where they actually design complete operating systems that are fully verified. But there the operating system is designed from bottom up to fit with some verification strategy. So obviously that's not the case of the Linux kernel. On the other hand, at the same time, we have tools, and the tools are presumably getting better and better as people are working on them. So maybe 10 years ago it was premature to think about verifying Linux kernel code. Maybe we could think about it again now that 10 more years has passed. But then, as I mentioned before, another wrinkle is that the Linux kernel is evolving all the time. And so you put in a huge amount of effort to verify your special function that you're very concerned about. And then next week someone submits a patch that is going to change everything, or next week or next month or next year or whatever. But it's going to be a continual effort to maintain these things. Sometimes they're new algorithms, sometimes they're optimizations, sometimes they're bug fixes, sometimes there's introduction of bugs, and so on. So the idea we had is that at least for some kinds of these changes, maybe they don't have much impact on the specifications. So if you think about optimization, I mean, in general, the specification is describing the input behavior and the output behavior. So you can think of the function as like a box. Its numbers come in, numbers come out, and there's some gears and stuff in the middle inside. And if those gears go faster, as long as you're still getting the same numbers out at the end, your specifications should still be valuable. So that's something we can hope for. Maybe we can define the pre and post conditions on one version and then use the same ones after that. So all of these things that FremSE offers, where it's figuring out what are the verification conditions by itself, it's using the SMT solvers to figure out those prove those verification conditions, all of that's going to help us. It's like you have the same specification, the tool will have to go in a different direction, but the tool will manage that by itself. So what we'd like to do is perhaps someday, this is like long-term goals, maybe prove correctness of Linux kernel code, focusing on core functionalities, scheduler, memory management, something like that, something that lots of people will benefit from. And then provide a pathway to porting these specifications from one version to the next. And then maybe someday when all of this is working smoothly and so on, maybe we can achieve uptake from the Linux kernel community. Okay, so what are we doing? We take some function and we're going to just focus on that one function. And that function may be referring to other functions and also to data structures. And so we may provide like some dummy definitions. We're just concerned with the algorithm of this function. Is it behaving in the way we expect? So we don't really care what those other functions are actually doing. We just want to describe what they should be doing so that we can reason about the function that we're interested in. And then we use FremSE, as I mentioned before, to manage the proving process. I just want to focus on the algorithm. I'm not concerned with all of the strange things that can happen in C code. Those are interesting problems and definitely hard work, valuable challenges, but I think that we can't just completely ignore all the algorithmic issues just because C poses all of these strange problems. So my assumption is that I can write these preconditions and say the world is a safe, happy place. Please tell me that this function is doing the right thing, at least in that situation. Okay, so we're going to look at this in more detail with respect to the function should we balance. So this is a function that actually I had an engineer, his name is Keisuke. He started working with me about 6 months ago. I needed an example that he could work on. I randomly chose this function. It's a part of the scheduler. We know a lot about scheduling, and it's a function, it's not too complicated. It has changed recently, so I thought there might be something interesting to do. But it's not a function that was chosen by design to illustrate this talk. So this is a function, the goal of the function is we have load balancing. So load balancing is the idea when a CPU feels like it's not doing enough work, it would like to steal some work from other CPUs. But it's undesirable from a kind of global system point of view that all of the CPUs try stealing things at the same time. Because if they all try at the same time, they're all going to try to steal the same things. And actually what's going to happen in practice is that poor task that gets stolen is going to have to move around the machine to all the different CPUs that try to steal it. So we want only one CPU to be stealing at a time. So this function, the code in the function existed before, but it was decided kind of isolated as a function in 2013. The first version of the function was not correct. So that's already a kind of a hint. When you make a new algorithm, maybe there's some chance that things will not work out as expected. The function was first released in Linux 3.12, and over roughly the subsequent 10 years, there were 10 versions of the function, plus one more that we proposed, several recent optimizations. So it's kind of not a really high level of activity, but things have happened. So just an overview of how the function works. The input is the core that is, the CPU that's trying to steal, and some other information about the other CPUs that it could steal from. Those are probably trying to steal as well. And then the action of the function is to elect. It's a little bit strange. It elects an idle CPU. It tries to elect an idle CPU that's allowed to steal. And then it looks to see if the CPU that is running this function is actually the one that was elected. And in that way, if it's the one that was elected, then it says, yes, you're allowed to steal. If it's not the one that was elected, then it says no. So it's kind of a distributed, sort of simple distributed algorithm. If nobody is elected, if there are, for example, no idle CPUs, then there's a default CPU that is chosen, and all the CPUs will choose the same default. And the goal is basically that only one CPU should be stealing at a time. So this is the definition of the function. You don't have to study it in any detail at all. Basically, I just go through the different parts of it. The input is an environment. It contains that information that I said, the CPU that wants to steal, for example. There is one case in which we always just let the CPU steal. If the CPU is newly idle, then there's the feeling that it was just working recently. It might have a high frequency. It's good to let it do more stuff, so we just always let it steal something. The main part of the function is this code here. There's a bunch of masks that suggest which are the CPUs that we could steal from. There's an intersection of those masks, and then there's an iteration, that's the important part. There's an iteration over those cores of those CPUs that we're allowed to steal from, to see if any of them, which one would be the best to be doing the stealing at this point. And in the last bottom line here, you see if nothing was selected, then we just use the default function. We just use the default CPU. And in the end, we try to see if the elected one, how the elected one relates to the one that is actually asking about whether it's allowed to steal at the moment. And so you can see here is the bug. In the last line here, the person put a not equals, and it's supposed to be an equals. And so actually in this version, all the CPUs get to steal except for the elected one, which is obviously not the desired behavior. But fortunately, this was never in a release. This just existed for a few weeks, and then somebody found the problem, and so on. So here's our initial verification conditions. Again, I don't expect you to study this all in detail, but the important thing I just want to point out is that I had these 3 issues. One of them is the newly idle case, one is the case where we find an idle CPU, and one of them cases where we don't find an idle CPU. And here for MSC, it gives a new feature that I didn't show before, which is you can define behaviors. So you have different, it's just a way of organizing your preconditions. You think about the different ways you can execute the function, and here we have one behavior for the newly idle case, one behavior for the case where we find an idle CPU, and one behavior for the case where we don't find a idle CPU. And we also have to do something that people who do verification are always afraid of. It's a thing called a write a loop invariant. So when there are loops are a bit complicated to reason about. It needs some help. It needs some help from the human. And so the human has to write some properties that are always true as we go through the loop. So this is just some more properties that the person has to write. So basically the idea, this is the initial version of the function. And so we could imagine perhaps that there's some verification enthusiast or something like that who will be writing these initial pre and post conditions for the function. And just as on our test machine, which is a fairly large server with a fairly large amount of memory, MSC proves this in about 1 minute. So we're successful. It doesn't take too much time. I think I can run it on my laptop. I don't think it would take much longer either. So everything was wonderful, but the problem is that, of course, the code is going to evolve over time, and all kinds of strange little things happen to it. If the function is created, here we are fixing that bug that was identified. We replace the not equals by equals. And then there's a bunch of different things that happen. Some are complex and some are not. Just to note that all of these versions that are in red had bugs in them. And one of those buggy versions is actually in version 6.6 and 6.7 of the Linux kernel. So the question is, of course, as the code changes, can we rely on developers to update the specifications as well? Is it feasible for people who are not verification experts to do that work? So sometimes we're extremely lucky. There's a change, and actually we can just use the specification the way it is. So the first case where that happens is there's one of the commits that just changes a bunch of comments. So obviously that has this like make things uppercase instead of lowercase or something. So obviously that has no impact on the proof, and we can just use our specifications as they are. But actually there's some other cases where that happens. This is a just kind of reorganization of the code. It was realized that instead of, you can return early with the result instead of kind of maintaining it, returning at the end. You can see a lot of lines get removed and added, but actually the input and output behavior stay the same, so we can use the same specifications. Another common thing that happens to these kinds of functions is you realize, oh, there's some kind of race condition I have to take into account or something like that. And so we get some new conditions that are going to be easily success or failure or whatever. So one of them gets added here, and what that translates into exactly is another behavior in the specification. So since the code change is pretty simple, the specification change is pretty simple also. Unfortunately, these behaviors are like if something happens, then we do something else. If something happens, then we do something else. There's no if then else in this language, and so we have to put the negation of the new if that we added in all the other behaviors. But it's still fairly mechanical. Maybe we could even automate this at some point. On the other hand, sometimes people actually change the algorithm, make it more clever in some way, and then more work is required. So I said we're searching for an idle CPU, but on a modern machine, not all the idle CPUs are created equal. So there's the concept of hyperthreading, and there's like these cores, and they're actually running maybe 2, or depending on the architecture, 4 different threads of computation at the same time. So if you have a core where some of the hyperthreads are actually doing things, that's an undesirable place to put more work. You would prefer to find a core that is entirely idle. On the other hand, you might not find a core that's entirely idle. So you might do a whole iteration and not find any idle core. You obviously don't want to go and do that whole iteration again, because these iterations, it involves searching, involves querying other cores about how busy they are. And so the clever thing to do, which happens several times in the scheduler, is to keep track of several things as we go through the loop. So we have the best one that we want, but we keep a backup one along the way. So this becomes much more complicated from a verification point of view. So basically, here it hurts our loop invariance. It's not the input-output behavior as much, although that is affected as well. Basically, we had one loop invariant that was describing our iteration over the loop, and now we have 5. That one line has turned into 5 lines. And those 5 lines are a bit tricky to make work properly. And then things get even more complicated when it was realized that once we find a core and we see that some of its hyperthreads are busy, then we should remove all of those hyperthreads from the future iterations with the core of the loop. And so things become much more complicated, and actually in part due to the complexity of the code itself, and also due to our lack of familiarity with Framatcy, because we were just starting with it really. This took us months to get it to work right. So that's not very encouraging, I would admit. On the other hand, we did find a bug. In exactly this same code that we found so hard to verify, there is also a bug, which is that it's something that's allowing it to, allows 2 different CPUs to be doing load balancing at the same time. And so the idea, the issue, the way you can kind of sort of see the bug, I mean, a disadvantage of verification is that its goal is to tell you that your code is correct. So it just says yes. It rarely says no. Instead of saying no, it says, I don't know. It says timeout. It says unknown. It never is willing to come out and say, this is wrong. So it's more like you hunt around for what is the thing that you can prove, and if you can only prove something that's different than the thing you wanted to prove, then maybe that represents a bug. So that's what happened in this case. The typical behavior here, you see it has an if and only if, so that's somehow good news. And the behavior that we are able to prove in those later 2 versions does not have the if and only if. We have to have 2 different conditions. So in the end, so these are our list of commits. We had our original version. Our original version had a bug. We had 7 versions after that. That was over about 10 years, almost 10 years. And all of those, everything goes smoothly. Either there's no change or there's some small changes that we could imagine that someone, maybe based on reading the log message, could figure out what they need to do to the proof. Or looking at the code change, they seem all fairly simple. And then we come to these last 2 versions, number 8 and number 9, and the algorithm changes, and in a very complex and subtle way, the proof time explodes from 1 minute to about 15 minutes. Things kind of don't go so well. But there was a bug, and there's actually also a missed optimization opportunity in that code. So maybe, I mean, at the conclusion, we could have maybe formal verification of Linux kernels a bit premature. The tools are progressing. They're usable by people who don't have 15 years of expertise in doing that kind of thing, but they're still not, it takes a lot of patience, and it's, the feedback, I think the feedback is not really great, and so often things don't work and you don't know why they don't work. You just have to kind of stare at it and think about it. There's nothing really to guide you in the right direction. We would like to study more histories of more different functions and try to understand, were we just lucky that those 7 changes were easy to verify, or is that kind of the common pattern? We can also think about other kinds of tools that would make the process easier to manage, to collect the dependencies. Some kinds of code changes, the change in the specification might be straightforward and automatic. Something to help you distinguish between easy changes and hard changes. Maybe it's not worth spending any time on hard changes. Maybe you should just call in reinforcements immediately. And also help in finding bugs. So identifying bugs, like when you're in part of this process, does your result indicate a bug or not, or what? So everything we have done is also available if you want to see the code and proofs and so on. So thank you.
Hi. I haven't seen the tool you're referring to before. Is it from my impression is that it's not imperative at all in how you express specifications. It's declarative or maybe functional. Is that true?
Declarative, yes.
Yes.
You say for all these things happen.
And what is the advantage? I think I know the answer, but I'm a question for what do you think is the advantage of having it very declarative?
What do you think is the disadvantage?
The advantage is because we worked with this 30 years ago in another completely different thing, is that you can actually formally verify your specification as well. With that kind of expression, it looks very talkative or complex, but it has certain advantages. I'm not an expert on it, but I worked in a group where some people convinced me of virtues of having it not if then else and so on, but having this very declarative. Because
yeah, I mean, I would make the point though that I'm not really completely sure to understand the whole declarative versus imperative specifications, because this is the only kind of, I've used other tools, but this is the only flavor of technology that I've used. So, but you can, like you have your code and you can put some asserts in your code, and so that allows you to specify things that are going along with the flow of control of your code.
So what we built was the declarative form of it was the basic lingua franca between certain tools that could have views against these specifications that we could express complex systems with. But we used it to drive the development, not to verify. But we could then verify the specifications because of the declarative nature of all specifications. So there are a lot of opportunity for building tools up on this that simplifies the work and gives you certain views, as long as you maintain the declarative nature of the underlying thing, but you can then have port between in the your text format between different generations of other tools.
Yeah, I agree. Yeah. That's interesting point of view. And I mean, I definitely agree that even in this case, I think I just have a little ... some here in my specification. I think the specification is definitely longer than the function. And some cases are quite extreme. I had a student, she was working on a 3-line function, and she has about 40 lines of specifications.
Yeah, sounds familiar, very familiar.
You shouldn't laugh so much. It's the 3 lines, it's a while loop, so it's a bit complex, and it's not completely trivial, but yeah.
Okay, thank you.
Just two things. Can you do anti-patterns so you can say that basically this should never happen?
Sure, yeah. You just say for all blah, blah, blah implies not X, yes.
And also, I was also wondering if you can define functions or like so you could reuse the CPU selection, for example, instead of having to do the for loops invariants, you could reuse something that defines the for loops for you instead. So you.
Okay. Yes, so that's an extremely interesting question, and I will, since I really enjoy this topic, I will tell you far more than you need to know. But yes, often you find yourself actually, if I can find my specifications here. Here we go. I have done that already. So here you see we have this thing, it's called relevant. And relevant is taking a bunch of masks that are referenced in the code, and it's putting some conditions on them, because I have to check them every single time.
Yeah.
Whenever I'm going over my iteration, I'm only interested in the relevant course. And so what you can do is, one thing you can do is you can define a predicate. So that's basically like a function from a logic point of view, and it returns true and false. So the disadvantage of predicates is, or sort of the advantage and disadvantage of predicates is that it, in terms of the SMT solver, it kind of reduces the search space that it looks at initially, because then you have a black box which is called relevant, and then it's not going to necessarily probe into that black box. Because actually SMT solvers have no idea what you're trying to do. They're just like these unoriented search things. And if it unfolds all your predicates, that would also be undesirable. So it's not really sure what to do. So in the short term, it just uses them as black boxes and tries to reason about them. And so someone over there suggested macros, and actually that's what I do.
Yeah.
Because with a macro, then I can control, the macro is going to get expanded. Actually, there's some kind of preprocessor for Fremacy that's going to expand the things even though these are in comments. And then you can kind of control what's the level of, there's like the level of viewing from the human point of view, and there's the level of reasoning from the solver point of view.
I just thought that it would be easier if we include these in the kernel, it would be easier for other kernel developers if they could just like use that macro for the things. Because
Yes, definitely.
in the later examples with the loop invariant, it becomes a lot of them.
Here we have a pattern which comes up in many, many verification efforts, which is like for all, and then we have some range, and then we have some, this is more for the range. It's like some good properties, but it doesn't have the property that we're looking for.
Exactly.
So we want the first thing with that property. So that's definitely something that one would like to encapsulate in some way. Just because it's so reusable. But we need more experience to figure out what are the things.
I just thought it would also make it easier for anyone else. If someone changes the function, then they can see, this is almost like the C code, but not quite, but I can still like derive what I should change because of my change to the code. So then it would be easier to maintain as well.
Absolutely, yeah.
Okay. I couldn't help but noticing, like, maybe this is far out, but since the Garmisch conference in 1968, like there has been like an emphasis on pretty much two ways to prove software right. One is exhaustive testing, and the other one is formal proving. And I think in the 70s, Peter Nauer is famous for having stated that programming is not a formalism or something along this line, and written several books on the subject, like, no, programming is not a formalism. And the ambition with this is pretty much to prove him wrong, right? At least partly. So it seems like there is the battle that is playing out is a little bit of like formalists coming from one end and trying to prove things right all the time, while there is like another camp of people who just like, just write more comments and tests. And that this is going to be like the strain maybe that we are going to see when we introduce this. Like, no, but like this is too complex to express with a lot of formal logic. You have to just like express it with some comments and then write some tests and be happy with it.
Yeah, so I think that there's sort of a continuum between proving everything and testing everything. And I think what I have presented here is not at the far end of that continuum, because I'm not, as I said in the beginning, I am not, like the C language allows you to address everything in memory, but I'm not allowing that. I'm just, the idea is that we set things up in a nice way. So that's one point. But I mean, like we set things up in a nice way. We, like my function calls some mask functions and stuff like that. I didn't verify them. They are involving bits and arrays of bits and stuff like that. I didn't want to, I don't know if Fremacy can handle that or not, but I didn't want to take the time to find out. I see this in some sense as more like bug finding, like just like Coverity or any of these other bug finding tools, but where we have a somewhat smarter way of propagating information. Like if you say x equals 3 here, and then you use x later, is x still 3 or not? And so, like coccinelle does nothing. Coccinelle has no idea whether X is 3 or not. Smatch makes some effort to propagate that information. That way it can do a bit more reasoning. I don't know what the situation for coverity is. Maybe it propagates some. None of these tools propagate everything, and so verification propagates a bit more. By forcing the user to make some specifications, it's able to push things a bit further. On the other hand, we could say that, I've been arguing maybe we can get kernel developers to take these specifications, update their code, update the specifications, and so on. Maybe that's not possible. Maybe, though, we could somehow use the specifications as a motivation for tests that we could then use in the future. So that could be another direction to take things.
We are in violent agreement. We can test. We can use formal verification where we can use it, and then when we can't, we just go with something.
So
it's
not
perfect.
objecting
It's actually,
to tests.
This Formula C, it's Formula C. It's actually similar to a tool called Polyspace. I think that was popular in the days back, and it's used in formal verification of, I don't know, military stuff.
Yeah. So it's the language. The specification language is fairly standard. There's other tools also that kind of do the same thing at the current time too.
This reminds me also of I had a bit of luck to talk a bit with Margaret Hamilton, known for leading the Apollo software effort in the Apollo days, when she was at ICSI as a keynote in Gothenburg.
Yeah, that was very nice. I saw that as well. Yeah.
And actually, we could agree that because her effort after the Apollo with Hamilton Technologies was very much about how to express actual programs in notations like this. And she worked many years with that, and she was so happy when I at least understood part of her intention with all of this. So it was a very heartwarming moment, because I know about fighting for your idea.
Okay.
And it was very close to what you use for verification. She wanted to express whole systems with that, based on her experience.
Yeah, this is a great discussion, but I think that was a nice note to finish up this session, because Gustavo needs also some time to talk. Sorry.